Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So, good morning. It's great pleasure for me to introduce Ron Hu will present the results from his 3-month-long internship here. The project is microphone array for audience capture in lecture rooms, and the mentors of this internship are me and Patrick from Conference XP team. It's a kind of joint project between Speech Technology Group in Microsoft Research and Conference, actually University Relations team in Microsoft Research. Thanks for coming.
Thank you. My project is the microphone array for audience capture in lecture rooms. Well, first to talk about our goals, our problems we're facing, and the solution we proposed. And next, we'll briefly talk about the 2D beamformer that we used. And then I focused on the SSL and its implementation. And last word, I talk about the experiments and results in future works. The lecture room contents are nowadays recorded and broadcasted over the internet because of the development of the media technology and network technology. But our means of capturing the sound are somewhat still very primitive, and the qualities are not satisfying. That's why we are trying to use microphone array approaches to get a better quality in sound recording. The sound source localization performance is very critical to the microarray beamforming system. It provides accurate source location estimation to the beamformer. We have an existing system that cannot solve this problem very well because of the large range of sound capturing in the lecture room. In the long range, the reverberation level becomes high, and the noise level becomes higher. The way we are going to solve, trying to solve this problem is just very simple. Just try to move the array system to the center of the lecture room. This one is the existing one, and it's somewhat far away to the audiences at that corner. By moving to the ceiling, we cut the range. But mounting on the ceiling, the problem has been changed to 1D beamforming and source localization to 2D problem. We need to develop both 2D SSL and beamformer and modify the calibration to 2D, and we have to improve the performance and scalability of the system. This is the hardware. Actually, the hardware are the same as the previous one. They all have 8 channels, 8 microphones. The outer 4 and are 20 centimeters apart, each pair, and the center 4 are 7.5. And we also have a wide range camera inside. This one currently is used for our experimental use to evaluate performance and to do to measure points, locations in the experiment. And in the future, we may use it to integrate video information to help sound source localization. The software we're using are DirectShow. We based our development on this platform, and the software D-Shoe filter that we developed are majorly three parts. We focus on SSL, and we implement some VAD and revise the beamforming. This is a block diagram of our system. The pre-processing in Beamformer and SSL all need preset either coefficients or array geometry, which is stored in INI data file, or the Beamformer coefficients weights. And source localization module is critical in this system. It will provide a source location estimation and to the beamformer. It also provides some confidence and standard deviation estimation. We have also evolved the calibration part, and just minor work for. Since now we changed the scenario to 2D, the method we're using should fit the 2D case, just a geometrical modification. The 2D beamformer actually works the same as 1D. It's a time invariant frequency domain filter in some type of beamformer. It's not adaptive one. It has a set of pre-computed beams. We use 13 by 13, which covers from negative 60 to negative 60, negative to positive 60, and spaced every 10 degrees apart. It's actually provided by the existing algorithm. But the beam scanning and selection scheme should be modified to 2D. This is a beam shape we are using. The width is actually very not very narrow. The strategy we use to change beams are mainly just very conservative one. We change beams only if some kind of confidence is large, and the new position estimation is far away from the current beam position. Next, I talk about the basics of sound source localization. There are mainly three types of methods. The first one is the time delay estimation based, which is very traditional one. It computes generalized cross correlation functions for each pair of the microphones, and in the computation we can use the weighting, for example, fat weighting or maximum likelihood weighting, to enhance the robustness. After we obtain the time TDE estimation for each pair, we can combine the information, the multiple pairs of the TDE estimation to obtain the source location. There are several methods in this part. I'll not focus on it. The second type is the beam steering. It computes energy for a set of beams, and then it scans the beam and find the maximum energy and do the interpolation to get a localization. We can also reduce computing time or speed up by some fine-to-coarse search approach. It is quite simple and fast and reliable, and we also extended it to the as a baseline to our system. The third type is a new one. It's based on the instantaneous direction of arrival. Direction of arrival is actually equivalent to the phase difference. We group the estimates of phase difference into n-1 dimensional vector, and do per beam SSL estimation to be combined by the post-processing later. For the scenario is the principle is like this. This is the geometry. Here we define this direction to be x, and this direction to be y, and this direction to be z. If we do some approximation in the far field, for far field conditions, this row is a range from the source to the center of the array, and these are microphone positions. And since we define x as in this direction, we here the microphone position has the x equals 0, and for our case with a approximation in far field, we can describe the distance, the difference of distances, which is proportional to the phase difference that we are going to measure. With the representation of polar coordinate, we can get a set of parametric equations. Actually, there are n-1 independent pairs, and we can show that this set of parametric equation actually forms a kind of surface in the n-1 dimensional space. We can see that this corresponds to a source in the direction of phi equals 0 and theta equals 0. And as we move, change the phi, the trajectory of the sources are located in this line, actually. And if we change the theta, then we're changing the trajectory are in this place. This is computed using the approximated the parametric equation, and this one are computed using incorporating the directivity pattern of the microphone this is a kind of engineering computation. This is theoretical computation. And which is also shown here is a simulated signal location, which may not be very clear. As a small red point.
In the back.
Sorry. Not okay. Yeah, here. The simulation is done like this. A 500 hertz tonal direct pass signal was generated, and at this position, and we can obtain its position here. This is ideal case: no reverberation, no noise. And for the partitioning of the space, we can be flexible. We don't need a high resolution for large phi and theta, and we actually are using a scheme that reduces resolution for high phi and theta which also reduces a certain time. This scheme also has a scalability because the trajectories can be computed online very quickly. We can change the resolution easily and to fit different requirements that is changed. And this method do not need to compute the beamformer coefficients offline. That's very time consuming. Here it shows simulation when the source signal is a recorded speech, and this is also direct path simulation, no reverberation, because simulating reverberated case is very difficult. We may need the impulse response or some other information, or use a simplified method. For example, the mirror approach. That's very a kind of approximation. For this case, because I think in this case we have a wider bandwidth, and the second we have sensor noise. In this case, we can see that the clustering distribution of the source trajectory can no longer be located at one point only. And another problem is the so-called phase wrapping or aliasing. When we measure this at a high frequency, we can see a wrapped phase because the phase information has a range from negative pi to positive pi. So this is inevitable. This is obtained trajectory from recorded real speech in my office. I cannot provide the precise location, but we can show from the density here. I was actually some point of negative phi and positive theta. Most of them are located near the surface, and the red ones are the signal frames, which is judged from the voice activity detector, and the green ones are just to be noisy frames, by the VAD. As you have seen that the distribution in real case is no longer a single point. the difficulties comes from first the noise will move them away from the surface, and the reverberation is a very annoying thing. It also moves them. The way we're dealing with this problem mostly comes from the post-processing or filtering, and we'll also do some weighting to overcome this problem. For the per-beam SSL estimation results, we need some kind of filtering. There are already some techniques in this respect. For example, particle filtering. But we did not use this one because it is first CPU expensive, time consuming, and it is adapted from a radar or some other maybe navigation system. Not very suitable in our case, because I've seen in their modeling they use some of them may use motion model, velocity, that kind of estimation. But for audience capturing, audience are most probably sitting down, not move. Yeah, okay. The clustering should be talked about because it's the approach we take. We extend it from the 1D real-time clustering technique. This is the architecture of the source localization processing. Because of the unreliability of the per-frame estimation, we need to do some filtering as a post-processor and to do some weighting to enhance its performance. I first briefly talk about the video activity detector. The existing one are based on this simple logic, which tracks a minimum energy or noise floor of the speech. This estimation, noise floor estimation, tracks the low energy, which is probably noise, tracks down very fast and tracks up slowly. So it keeps the floor information. And then we apply a threshold for binary decision, or we can use hysteresis, or it's a term from physics, or it's also maybe similar to a two-state finite state machine. Yeah, okay. If currently we're in the noise state, the threshold to change from noise to signal can be set at a higher level. But if in a signal state, the threshold from changing from signal to noise can be set lower than the above one. Actually, both ones are low. In our case, are not very high, because we intend to deal with long-range problems, and long-range SNR can be low. The second VAD we implemented is the soft decision based one, which computes a likelihood ratio per frequency being. We find it good information because we may need this later for the weighting of the per being SSL estimation, or per being the distribution modeling. in our IDOA-based method. This scheme also applies a Hanover scheme, which is kind of not a 2D finite state machine, but a two-state hidden Markov model. It assumes that a larger transition probability to stay in current state. And in this paper, it also we can also obtain these information. This is our baseline. First, the baseline in 2D. These are the modification we did from 1D. The first is the same. The only difference is the dimension. The second, we need a new biquadratic interpolation, which we did not have. And in this interpolation, to get a SSL estimate, there are some detailed problems because the biquadratic interpolation in our test we cannot. This method we need to avoid some saddle point problems. And the beam steering based method also could provide a confidence level measure. We use the contrast of energy distribution of the beam energy, which is defined as this ratio. If the distribution of the energy is very picky, this means that the current estimate is reliable. For the baseline, we also tested the fat weighting technique, which normalizes or widens the input before beamforming. This technique actually improves the robustness to the reverberation. Our new method for the estimation of IDOA, Ivan Tashev in this paper modeled provided us with a model of the spatial probability, and then based on that, we measured this with we weighted the probability, trying to improve the reliability of the SSL estimate, and then we do the same thing, choosing the maximum. Is there any other good weighting techniques? So in the current system, we try to evaluate the possibility of using a more generalized measurement. Here we add some. This is the combination of these two parts can be regarded as weighting. For the G, we actually tested two choices. This one is actually a new one. This is from the 1D case in this paper, but this measurement is after noise suppression. And the second term, we also tested too. We tried to incorporate the speech presence probability, which is provided by the soft VAD technique. And this can also be set to 1. And for the spatial probability modeling, and we can use this model, or we also tested a simplified one. We call it simplified WIDOA, which is just choosing maybe it should be maximum, the maximum point of the point that maximizes this probability estimate. In the implementation, it's kind of minimization, because we choose the point that is minimum, that has a minimum distance to the source trajectory location. Okay.
So when you say you're combining all bins, do you mean that you're combining the SSL estimates from different frames?
This is for per bin estimate only. Weighting is for per bin, per frame. Sorry, per frame.
Just a moment. For every bin, is performing the sound source localization. Practically, we know where is the estimation for direction estimation for every bin. And what he discusses here is how to combine those 256 or 320 bins into one single estimation for the frame.
Or for one frame?
Yes.
If the frame basically meets the criteria, that we have some signal there, which comes from the voice activity detector. So this is exactly, those sums are actually combining the per bin estimation to per frame estimation.
And we also have a range of this combination. We actually are only interested in the speech part. No other parts. In the implementation, we use 300 to 3500 hertz. The post-processor will take from the per frame SSL estimator the direction and some kind of confidence, and it keeps all the measurements from the last 2 seconds in a relatively long queue. It will form a kind of bucket in a 50% overlapped fashion, and we choose a cluster with the higher sum of confidence levels, and then we compute the statistics, the location mean, which is comes from the samples that are within this bucket, and provide a standard deviation estimation for that estimate. The measurement, a measurement of confidence level is also provided by the post processor. This confidence level is used for for steering beams and displaying purposes. It's based on 3 factors. For example, number of measurements used, the age of the latest measurement that we take, and the standard deviation we computed. We did some evaluation experiment. The performance evaluation are based on the 5 recordings of single sound sources. We also recorded 2 sources, but it's more difficult to evaluate because our time is limited. For two sources, we need kind of a labeling more complicated than this. We did, in our evaluation, we did one file processing, and it's done offline, and we just record the per frame SSL results and post-processor SSL results, and compare the bias and standard deviation. We are lucky to have to be in the same room as we did the recording, and these are the choices of location. The method we use to locate the mouse is a somewhat primitive one, maybe not very precise. We use a camera. We first measure the height. This is how the array is mounted on the ceiling, and this is pointing to the floor. We first measured the height because this is fixed, and then for those choices of locations, we compute the coordinate of those directions on the floor. We get corresponding points on the floor, and then we move the speaker, let its mouse overlap with that point on the floor. We do this on the screen with the help of the camera. This is simple, but since the measurement of a range of an installation may have some errors, so this may not be very reliable. And here it shows the coordinates we computed that's located on the floor, and these are recording conditions. These are computed by averaging all 8 channels. This is estimate using the existing SNR estimation tool. The average is 9.3 dB approximately. As I said, our ground truth measurement are not very reliable. This is verified by our evaluation of the SSL mean. All the methods, all the SSL measurements have a consistent bias, which is smaller than our so-called ground truth. This is our analysis for the bias. How, in the future, maybe we need some kind of accurate equipment for the measurement of range and angles. So our comparison and the evaluation are mainly based on the standard deviation results. These 6 cases are IDOA based. No A means no amplitude weighting, and amp means with amplitude weighting. No P means no probability weighting, speech presence probability, and prob means with speech presence probability weighting. And S is the simplified one we tested. And for the simplified modeling, we did not test no amplitude weighting because the results are similar. And this comes from the per frame estimation, per frame results. We can see that without post-processor, the no amplitude weighting and no probability seems to achieve the best result.
Why amplitude weighting, no probability is the best? The fourth line. I'm looking at the average.
It's actually probability. Sorry, it's probability is it's the best. As we can see, since the SNR is for these three cases are not actually for these two are not high. Using speech presence probability, we can improve the accuracy compared with the method without using probability weighting. The average also shows this, but for the weighting with amplitude, we do not see this. We do not see this. I think this might be caused by the amplitude also bears some information on speech presence. If the amplitude is high, then it's they just have some overlap of information. But interestingly, if we do the post-processor, we can see that the beam steering-based algorithm, the baseline is actually improves a lot, and the fat-weighted beam steering is also very good. And with post-filtering, the first one seems to be performing the best. Actually, they are very close. They're very close. Next, I show some demos. Some intermediate results. This one. This visualizes the distribution of sources in the IDOA space. It's very noisy. And at higher frequency, we observe phase wrapping. And next is how the post-processor works. This shows the number of samples in each bucket. We can see that as one move from one position to the other, as the source shifted, the number of samples in the bucket changes gradually. These samples are counted from the long queue. I'm not sure if I can find the video that corresponds to this one. Office room. Office room, maybe this one. Testing, testing. 1, 2, 3, 4. Hello, hello, testing. 1, 2, 3, 4, 5. Hello, hello. I'm here, can you hear me? Good. So we can see that as I move, the bucket goes up and down. And then, next, the evaluation results. The little prince went away to look again at the roses. "You're not at all like my rose," he said, "as yet you are nothing." This case is much more simple because simpler than the case. He was only a fox like 100,000 other foxes, but I have made him my friend, and now he is unique in all the world. And the roses were very much embarrassed. "You're beautiful, but you're empty," he went on. "One could not die for you, to be sure. An ordinary passerby would think that my rose looked just like you, the rose that belongs to me. But in herself alone, she is more important than all the hundreds of you other roses, because it is she that I have watered, because it is she that I have put under the glass globe, because it is she that I have sheltered behind the screen, because it is for her that I have killed the caterpillar." Okay, maybe you can see some marked points on the floor. We actually first, Benjamin helped me. He will tell me, move left, move right, a little bit.
Do you want to place your mouth over the cross?
Yes, actually, you can see here it's also a cross, and behind me there is a cross. But this one may not be very accurate. Since when I calibrate, I'm looking at the camera, but when I read,
the geometric distortions of the lenses are well visible. This is a wide angle lens, so
yeah. And this scenario is simpler than what we'll show next, the real demo. Because first, I'm sitting there still, no moving, and always there. My head seldom moves. And second, the range is not extremely long. This is from IDOA based method, and the baseline. Maybe we can see some difference. The little prince went away to look again at the roses. "You're not at all like my rose," he said, "as yet you are nothing. No one has tamed you, and you have tamed no one. You're like my fox when I first knew him. He was only a fox like 100,000 other foxes, but I have made him my friend, and now he is unique in all the world." And the roses were very much embarrassed. "You're beautiful, but you're empty," he went on. "One could not die for you, to be sure. An ordinary passerby would think that my rose looked just like you, the rose that belongs to me. But in herself alone, she is more important than all the hundreds of you other roses, because it is she that I have watered, because it is she that I have put under the glass globe, because it is she that I have sheltered behind the screen." And
the standard deviation is less stable. Basically, you have larger variation
in
the circle.
The circle is larger.
And it's, in general, larger than the final method.
Yeah. This one is very close to the first one. The little prince went away to look again at the roses. "You're not at all like my rose," he said, "as yet you are nothing. No one has tamed you, and you have tamed no one. You're like my fox when I first knew him. He was only a fox like 100,000 other foxes, but I have made him my friend, and now he is unique in all the world. And the roses were very much embarrassed. "You're beautiful, but you're empty," he went on. "One could not die for you. To be sure, an ordinary passerby would think that my rose looked just like you, the rose that belongs to me." Because some comments on the fat-based beam steering, fat-weighted beam steering, is that the performance under reverberation is better than the baseline beam steering. But if I remember correctly, in Yang Rei's paper and some others, it's not very robust to noise. Yeah. And maybe next I show you the real demo. Oh, I think I may need to turn off this because it's pointing to.
Testing. Point to me.
1, 2, 3, 4. Hello. Testing. 1, 2, 3, 4, 5.
1, 2, 3. Point to me. Here.
As we can see that as I speak longer, it can collect more information in the queue. Then the accuracy can be higher. But we can see that the response speed is also very, very good. Not very large delay. Turn on this because it's pointing to the speaker. Hello, testing.
1, 2, 3. Testing. Point to me. The main switch is here.
1, 2, 3, 4. Hello, testing. 1, 2, 3, 4, 5.
1, 2, 3. Point to me. Here.
As we can see that as I speak longer, it can collect more information in the queue. Then the accuracy can be higher. But we can see that the response speed is also very, very good. Not very large delay. The beamforming, the SNR improves a lot, but
so hold on. It's a 22.86 dB. You have signal to noise ratio on this now on the output you're just listening to.
What do you mean?
22.86 dB is the signal to noise ratio of the output signal.
Yes. It's much better than what is captured for each microphone.
It was around 10 dB here.
Yeah, but we're not maybe using the best noise suppression, spatial noise suppression technique. That part, I think, will be done by Binjun. Yeah. Okay. Sorry. The evaluation shows that the performance of the improved algorithm is good for the practical application, and we extended the IDOA algorithm to 2D. We modified the existing framework of localization, and beam scanning and steering. The implementation is totally real time. As a future work, I think we can integrate this technique with we should test other microphone array processing methods and test the system under more realistic conditions. For example, the scenarios with real conference, real lecturing, and is it possible to integrate and testing that in Conference XP software? And currently, we do not use the video processing technique because the range of camera cannot cover the whole range of beam scanning. But it helps for, it's only used for camera capturing, calibration, and position localization. In the future, we may use this information to be fused, a kind of fusion with acoustic localization method results. And for the real broadcasting application, we need to incorporate a echo cancellation module, which is only a placeholder in our module. We do not implement that. Today, I cannot show you the real broadcasting. We cannot connect this one to a speaker because it will be howling. Okay, these are my references. And do you have any questions?
Questions, colleagues? No questions? So then let's thank Laurent for his presentation and his demos.
Thank you.
And it was a real pleasure.
Thank you.